All right. And this seminar, as usual, takes place every Friday at noon Eastern Time and will be hosted on the Qiskit YouTube channel. So you can always go back, rewind, and look at parts of the video you want to take a look at again. So I know I always find myself doing that quite frequently. All right, so I think with that, we are ready to get into it. So I am your host, Zlatko Minev from IBM Quantum Research, and it is my pleasure and privilege to host Javad Shabani, professor at NYU today, who will talk about progress in realizing novel qubits with Josephson field effect transistors. Hello, Javad. How are you today?
Hi, Zlatko. I'm doing fine.
Good. Where are you tuning in today from, Javad?
From home, actually, in Westchester, New York.
Familiar place to me. And maybe I'll give a few words about you before we pull up your slides. Professor Shabani received his Ph.D. from Princeton University in 2011. After 2 years of research on semiconductor-based qubits at Harvard University, he joined UC Santa Barbara. There, he worked closely with Microsoft Research on hybrid semiconductor superconductor heterostructures to study topological superconductivity. Javad is an expert in quantum materials and devices for computation technologies, and he's currently a professor at NYU. On maybe a slightly more personal note, since I happen to know Javad, he's also great with outreach, Qiskit summer camps, uses PyPR and many more things. So it is my pleasure to welcome Javad. And maybe Javad, we can pull up your slides. And folks, this is the usual interactive format, so please do ask questions in the comment sidebar. And with that, it's my pleasure to turn it over to you, Javad.
Thank you, Zlatko. I'm thrilled to be part of this seminar series. It's a fantastic series. I've been following up on it on YouTube. I've been learning a lot on different subjects here. So today, I want to tell you about sort of new technologies that we may want to think of when we do quantum computing, especially for hardware-level qubits. My group at NYU, I guess you see a photo of them here. It's kind of outdated, but it's obviously an effort of a teamwork with many people involved. So let me just try to set up the problem and then tell you why I think the way I'm thinking, and hopefully I can motivate you about the challenges and advantages of the approach we're working on. So this is a slide, I guess, from the book Singularity is Near. And basically, it attempts to tell us how the computation is marching forward. So on the y-axis, you have a figure of merit of how we are capable in doing computation. On the x-axis, you have the number of years. And as you see, in the last 100 years, we have been constantly improving on the computational power, right? I guess in my age, I'm very familiar with Pentium 1 to 4. But if you notice, around 2010 and 15, even for the younger population, you see that the CPU speed is not getting faster. 3.5 gigahertz is pretty much the limit that you can buy. What you can do better is to basically have parallelism, like you have to dual, quad, and that way you can get more computational power. One thing is very interesting about this graph that I really like is that you basically go from a technology to technology, and then we kind of jump in terms of the power. Like you go from vacuum tubes that were very popular in World War II in the 50s, 60s, you go to transistors, and immediately the computational power make a jump because we have come up with the new ideas that enable new calculation power, right? So there is a hypothesis, which, how valid is that? I guess we can discuss it. But the philosophy is that, around this time, maybe 10 years from now, maybe 20 years from now, there will be another jump from what we have right now. And that next jump could be optical, quantum, DNA computing. But that jump is also interesting because according at least to this book, which I'm not sure if we should get it quantitative, we are getting very close to the complexity of a mouse brain. And then you can sort of think of all sort of stuff with AI and machine learning and can machine decide or not. But as a scientist, I think the fact that we are close to one of these revolutions is very exciting. And obviously, one of my goals in research is to make that happen, right? But if you also put aside the power of computing for a second, what is thrilling us, I guess, is very strange is the power consumption, right? The project, I guess, Blue Brain playing chess with, a human master. the AlphaGo game that basically Google tried to build the master. If you look at the power that is consumed between the two players, like a brain takes about 20 watt of power consumption, and a machine that basically has to calculate all the possible optimization path, it takes about 150 kilowatt, right? So the amount of power we are spending is enormous to do the same kind of calculations that a human brain does, right? So kind of making the jump may also help us with a more efficient way of doing computation. And hopefully that will be just a byproduct of what we will find. I'm obviously doing quantum computing, so that's why I want to motivate it here a little bit. There are kind of problems that immediately we will benefit from, right? I mean, some are basically security and cryptography related, right? You can actually encode the information in entangled states. Then it will be very difficult to break them. There are ideas like teleportation and others. There are things like quantum chemistry, like things that are in nature quantum, and quantum computers are very well suited to solve those problems, right? It's always there's a mismatch if you want to classically simulate a quantum problem. But if you have a quantum machine, you can try to simulate the chemistry that is needed. And that's probably one of the first targets that will be attempted in quantum computing research. There are other ideas around machine learning and NI, but also want to highlight the weather forecasting. So there are some problems that quantum computers can solve a lot faster, exponentially faster compared to a classical computer, which is phenomenal if it happens. But there are also problems that they can do slightly better. And if you think about weather forecasting, right, if I want to know the weather tomorrow, right, if a classical computer can do that in 48 hours, it's not very useful. But if it's quantum computer, I can get it in 6 hours. That still can help me whether the hurricane is going to hit my house or not, right? So there are problems at all different levels that could become very interesting and life-changing if we can sort of figure out how to do proper quantum computing. So I guess Zlatko said I was at Harvard trying to develop spin qubits on semiconductor. That was around 2012. And I remember toward the end of my postdoc, this article was published in Economist, Quantum Computing, an Uncertain Future. I can't remember what was the number of superconducting qubit at that point, but I think it was 2 or 3 qubits. Spin qubits were 1 or 2, depending on how you look at it. And the report was basically saying, whether these things will ever move forward, what are the challenges, how can it happen? It looked grim, but if you have heard, in 2019, now we have 50 plus qubits. There are groups that are claimed to have demonstrated, hard calculations, whether we want to call it quantum advantage. I think it still is yet to be determined, but definitely the game has changed. We have very powerful machines. IBM provides free hardware on the cloud that basically anybody can access it now, right? This was not the case 7 years ago. So I think 8 years ago, and I think there has been tremendous amount of progress just by staying on the path and being focused on the science of this. If you look at the startup companies, I just took this from CB Insight, and it's also outdated. It's 2016. You see that basically around 2000, this whole thing starts from Shor algorithm and the promise of breaking the RSA codes and internet. But then it turned out that problem is very difficult, but then a lot of other things sort of pop out. And the same thing, companies started growing very fast. And if you look at it right now, I think there are more than 50 companies focused on this kind of topic. There are big tech players like Google, IBM, Honeywell, Amazon, Intel, Microsoft, in addition to those startups. And each basically have taken a technology and try to basically perfect it as they go. A lot of main players and I guess hopeful candidate is based on the superconducting qubits. This is a solid state approach, and the scaling part seems rather more straightforward compared to the other approaches. And that's where actually my background in physics and superconductivity also resonates most with this kind of approach. So I will tell you how we are thinking about that. But I should warn you before I get to my talk is that at least in the field of quantum computing, this is how I see the landscape. I mean, you're kind of here, and I can see the next 6 months. I can see the next year, maybe with some dash lines, I can see the next 2 years. But after that, if you ask me, what are you going to exactly work on? I think it's very difficult to say that right now. It's just as we go forward, we kind of see more and more during this fog. And that's why I think it makes it a very, very interesting problem. So I love quantum computing research because of two main reasons. One is that it brings a lot of things together. If you think about it, material science is an integrated part, at least in the solid state solutions. You need to know a lot of physics, interesting quantum mechanics. You need to do microwave engineering. You have to do perfect nano device engineering. You have to do really good algorithm, and then you do the programming, right? And all these fields have to be at its best, right? We can't just do a normal material science. It just doesn't work. It has to be perfect. Like the coherence forces us to make the best materials we can. In terms of microwave engineering, we cannot even lose a photon. It has to be perfect again. So that basically all these fields together in the best shape that they can ever be really construct the basis for a really good field. I guess now we call quantum computing. It's also, in physics, where we do a lot of other experiments also in my lab, it's not only about a cool demonstration, right? There are lots of times that we show there is a very interesting fundamental physics, but then we kind of move on to the next interesting problem. Here, we need to get it to work, and it's for good. It could be life-changing. And I think these two make it a very different problem than the other standard problems. So hopefully you're all familiar with qubit and how we basically present it on a blockosphere. For a single qubit, just instead of having a 0 and 1 like a classical qubit, you have a blockosphere. And basically the vector in that blockosphere shows what the state is. Basically, it could be in a superposition of North Pole and South Pole, or 0 and 1. At hardware level, we don't have a perfect two-level system, right? I have some sort of a harmonic oscillator with some unharmonicity, at least in superconducting qubit. But if I can sort of isolate the state 0 and 1 and sort of shine a frequency that matches that level, then the other levels maybe become irrelevant. And basically, I can ignore them. And in a very simple case, I say my qubit 1 is level 1 and level 2, right? But having a single qubit doesn't really introduce us to quantum computing. The quantum computing currency, the money, the thing that you can spend is entanglement. The power is entanglement of qubits. If I can entangle 10 qubits, that's great, right? And it obviously starts with 2. So if I have another blockosphere and another kind of frequency that I want to put next to it, the way that the physics work is that you want it to be on the same order of frequency range, right? If you are in resonance, there will be some interaction, whether this is coming into a CNOT, swap, right? There are lots of different versions of this that can come in, and this very primitive cartoon is showing that, right? If I have a qubit at a different frequency, like the other higher states, then there will be no interaction. So I have one isolated qubit on this side, one isolated qubit on the other side, and no interaction. No interactions mean no entanglement, no quantum computing currency. So that's not very good. So we can optimize. We can have it close enough so they can interact for good reasons, and then be isolated enough so they don't start interacting in the wrong way. And if you have a frequency bandwidth, I can put so many qubits with so many optimum frequency gap. And as you see, eventually I will run out of space, right? Depending on what the numbers are. And this is mainly because I assume that the frequency of my qubit is very fixed and it's not tunable. So in some other ways, I can basically say, the fixed frequency qubits are like a diode. They're like a two-terminal device. And then I want to introduce you to a three-terminal device where things can actually be adjusted ad hoc with basically in situ gate voltages, very much like a transistor. And that brings, I guess, some good news and some challenges, and I will go through those. So if you really zoom in at the transistor of what is basically the basic element of quantum computing, on the left-hand side, you can see a Josephson tunnel junction, which is basically the core of all the qubits, at least in superconducting qubits, right? And it's basically a superconductor, an insulator, and a superconductor. It's a two-terminal device. And but if you change the insulator with a semiconductor, which I'm showing it on the right-hand side, you can now, because it's a semiconductor, you can change the conductivity. You can make it very insulating or very conducting with a gate voltage. So effectively, it becomes a three-terminal device, and you can call it a Josephson field effect transistor. And the properties of this qubit or Josephson junction, which can be put in the qubit, are not tunable. But there is always a dilemma in the quantum computing field, and I guess we should be aware of it. So here I'm trying to basically put it in simple words. To compute anything, entangle, to do more complicated algorithms, we need gates. We need interactions, right? If we need the interaction, that means it's not only between the qubits. Also, when I write a program, I have to externally drive the system. So I need a path from my computer to the qubits to actually do the calculation. That path can bring noise, right? So that's inevitable. If I want a perfect qubit, if I want a qubit that has the longest coherence time and everything, I can basically remove the environment noise by isolating my qubits. But then the disadvantage is that I cannot control them. I cannot do any gate. I cannot do any algorithm. So sometimes it becomes very confusing when you see an isolated qubit has a coherence time of, I don't know, millisecond or second, but that qubit may not be operable for basically doing fast interactions. Right, so everything is kind of perspective, and I will introduce you to the quantum volume criteria. So basically, we have fixed frequency hardware. That's basically shown on the left-hand side. That's the standard transmon circuit that a lot of people use a variation of this. And the tunable version is basically just removing that Josephson junction with Josephson field effect transistor and adding that extra one terminal to this, making a three-terminal controllable device basically does the trick. But what we should be careful when we do this, and that's actually what we do in my lab, is that one more terminal could also mean one more channel for noise. But there are advantages, right? Now I can basically remember when the frequency had to be the same for interaction. If I have that tunability, I can make the frequencies the same for 1 nanosecond, for example, to get the qubits talk to each other, then separate them into isolation. Whenever I need it again, I would bring it back with a gate voltage. So I would definitely win in terms of the tunability and the way I can do my algorithm. The challenge is that now I'm introducing noise through that gate voltage channel. And basically right now in our lab, we're looking at this kind of trade-off where it is very important for the qubit to not introduce noise into the core of the qubit, right? Because that's where all the action is happening. Another way to look at this Josephson field effect transistors is that they act like a switch, right? I can turn them on, I can turn them off with just turning on from an insulator to a conducting channel, right? And maybe if I don't put that Josephson field effect transistor in a qubit, and instead basically make it like a coupler in my resonator, for example, as it's shown here, I can basically store information on the far right-hand side, which is basically a high-Q resonator, and separate it from the left-hand side where there is a transmission line, there are noise coming down the system. And then you can imagine basically I'm isolating them when the switch is off. And then when I need to read the gate, basically I synchronize it with a readout circuit and I open the switch and then I will read the information, right? So that could be kind of a much more immediate application for these Josephson field effect transistors that I'm advocating for in addition to the qubit. And that way you can actually make a memory. And here I'm showing you that with pulses, you can actually synchronize the DC output and the RF input and to read and write into this resonator, the high quality resonator, by just tuning the gate voltage at the right time, right? So if that is possible, you can think of, I mean, a lot of times you're focused on the quantum processor, right? But, you know, in a classical computer, you have the processor, you have the memory, you have the ROM, you have all these other little peripheral devices around the processor. So here we basically have are arguing that you can actually scale this up into the quantum memory, and somehow a classical random access quantum memory, the access is classical but information is quantum, and you can maybe make up to 16 bit or maybe even 32 bit, depending on how you basically wire bond this. And there's a technology of how we can do flip chip and scale this up that basically can work with the hardware on the qubit side. So if the qubit is gateable, that's great. If qubit cannot be gateable, you can still use this tunability at the hardware for other applications.
Quick question, Jay, about the picture on the right. Is that the B picture is, I guess, the concept picture, but the top left is more of the current state with simulations of a planar chip as opposed to interposer?
Yes. The top left is the HFSS calculation to show that if you turn on and turn off the Josephson junction into a resistive mode versus a superconducting, can you still do the readout circuit? And it seems that it's working.
Mm-hmm.
The paper is on arXiv. if you want. I guess I forgot to write it here. It's submitted for publication.
Mm-hmm. Very cool.
Yeah. So it's basically a switch. And then the nice thing about this is, in the superconducting world, the squids were always the tunable circuits, right? And for a squid, you need some current to actually tune the magnetic field inside the squid, right? Here, I have just the gate voltage. Let me just go back for a second. Here, you will see that the gate voltage on the transistor, it never draws current into it, right? Basically, there is a dielectric that always separates the gate from the semiconductor. So the current is zero. You're applying some voltage. So the power that is consumed on that qubit or device is practically zero, right? It's zero sum time voltage is zero. So it's and because it's voltage, you can operate it extremely fast with the RF electronics that we already have in the lab. So that's one way. But the thing is, if you look at the quantum volume, if you want to make a real device, we want to basically maximize minimize error, maximize the quantum volume, and there are many ways to do it. I guess this I've taken actually from the IBM reports recently in 2017. The current state of industry, like IBM and Google and others in superconducting qubit, is that the error rates are getting to 10 minus 2, 10 minus 3. And I guess this is a 2-qubit error gates, which is more important than a single qubit error rate. Mm-hmm. And if you add the third terminal, you're basically introducing noise. There is a whole baggage of things that come with it. And then the errors go up to 10 minus 1, which is basically in this table, we can't even see it. And it basically makes it very difficult, right? So there is my research, actually, part of it is on making these 3-terminal devices better for qubit. But the way that we are saying it is actually works much better for couplers and basically things like the quantum memory that I showed you. The other approach is that, okay, what if we could basically go really down into this table, right? If I can get error rates of 10 minus 5 or 10 minus 6, then that would be wonderful. And that's the other part of the research that will come in. So imagine my tunable qubit or the standard qubits, we have many of them with a moderate error rate of 10 minus 2, 10 minus 3. Right now, to get to fault-tolerant quantum computing, which is the ultimate goal maybe for the next, 20 to 50 years, is that we need to do error correction. There is no way around it, right? Unless the error gets to below 10 minus 6, we still have to find ways to error correct. And one of the ways that one can do is to put a lot of qubits, the physical qubits, with this 10 minus 2, 10 minus 3 error, and make a qubit that is fault-tolerant, right? Just one of them in exchange for thousands or a million of these qubits. So that fault-tolerant qubit, the logical qubit, basically is almost errorless. And there is a way to do that, which we call surface code error correction. That basically puts this overhead. So in this example, which I picked from this paper by Vanier et al., basically shows that you need about 500 qubit in this picture. All the little dots are basically qubits that are doing different operations. Some are auxiliary, some are measurement qubit. And what is called ZA and ZB are the voids that you make in this lattice. And by moving them around each other, if you follow basically the pink line, that will become equivalent to a fault-tolerant operation, right? So there is an overhead if we cannot reduce the error, right? And if we can make a good logical qubit, then we do not have that overhead. So that's kind of the game that it's been. So then I can turn around the table and say, look, maybe I can find a physics, go to condensed matter physics, just deep dive, and I have a new particle that can actually does exactly the same thing that we are trying to emulate or simulate with the surface code, right? So these are stars on the right-hand side, the blue stars and the green stars. Let's say they are called the new particle, which now we call them Majorana fermions. And somehow I get to the level of the control that I basically discover these particles, make them go around each other, braid them. You can show that the result of the braiding operation will be very close to what you can actually do with the surface code. So let me see if these things do exist and what do we need for them. So for a general background, basically the first possible candidates were in neutrinos. Then in 2012, people thought that they can actually find them in condensed matter system that I will talk a little bit about. It turns out once you kind of have them, you have to follow knot theory because all the braids are happening in a degenerate ground state. So basically you can only track the phases, so you basically keep track of all the braids and knots. But the key requirement for this is that these particles have to have non-abelian statistics, right? So what is non-abelian statistics? Let me just spend a few slides on this before I kind of go to the experiments. So imagine I have n particles on my desk, and then I try to basically get particle I and j and swap them, right? And if I do it one more time, I basically get to identity. And what basically I'm showing here is that this projector operator to the power of 2 is equal to 1. If you want to express it in terms of the phases, this phase, the exponential basically is plus or minus 1. And you can basically track it to be a 0 phase, basically nothing happens, and that becomes a bosonic system. Or you basically pick up a minus sign, which, or theta equal to pi, that basically tells you you have a fermionic system. And that is very popular in the condensed matter textbooks, right? So when I do this exchange on my desk, if you basically plot this exchange as a function of time that is going in the y-axis, basically what is happening is that the particles are coming up out of the space and then basically rotate around each other. And that is what I'm trying to actually plot in the middle graph. And that phase, as we mentioned, it could be 0 or pi for bosons and fermions, right? If you can get any other angle, if you basically find a particle that when you do that, you basically get a general angle, pi over 3, for example. Those particles are called anion. Basically, they can get any phase, right? And there are candidates for them in quantum Hall regime. The Majorana fermions are another one that I will introduce later. But another very curious thing about this physics is that it's only relevant for d equal to 2 dimension, right? Because imagine in a three-dimensional space, if I basically move around one particle around the other, right? It really depends on the observer. If you're, I don't know if you can see me now, but if this is one particle and this is the other one, and I basically go around it from where you are actually projecting from your screen, you do not know when I was exactly in the same plane or I was actually further out, and you just saw it that I'm going around the other. And you can actually prove this rigorously that it is not possible to get this statistic that we want in dimension above 2. But in dimension exactly at 2, you can show that what I'm showing in the lower graph, if you basically braid 2 and 3 and then 2 and 1, and versus 1 and 2 and 2 and 3, the result of this braiding operation is not exactly the same. So you basically draw it on the paper, you will see that this is a very unique excuse me, a statistic with a very particular phase that you can follow. So if that is the case, the result of these two braiding is not the same, then you basically have non-abelian particles. So remember, if we discover these materials, we need to move them around and show these are non-abelians. If they are non-abelians, I may be able to make a topological qubit that is errorless. And that's kind of the game here. So to do that, I said we need to discover this exotic material. And the foundation for the theory work of this was basically proposed by Kitaev in 2001. And he basically said in one dimension, you may be able to actually create this Majorana fermion. And in the graph that I'm showing on top, you basically adjust the correlations between each pair such that you have basically isolated pairs or half fermions at either end of this one-dimensional channel. And then you can think of those two stars that I showed you with an imaginary dotted string in the middle, and then we can basically start braiding things around. So if you ask, what do we need? Can we just go to nature, mine a p-type superconductor like aluminum that we do? The answer is no. At least we don't know for sure that it does exist in abundant in nature, but the theory has given us a recipe to engineer this. You need a spin orbit, Rashba, you need in-plane magnetic field, you need proximity-induced superconductivity. We do not have all this in one single material, but I can find superconductivity in many materials, including aluminum, or a spin orbit in semiconductors like indium arsenide, right? So maybe if I can put them together at that interface, basically I can borrow the properties of aluminum and indium arsenide. So if the interface is perfect, there's a very good chance that I can actually create this state. Once I have it, you can actually go through details, and to do a gate, you basically have to do a lot of braiding. And there are lots of interesting, actually, theoretical proposals of how you can make a CNOT or simpler gates. So first, I need to show you that I can realize this system, I can make these interfaces, and how we can go from there. So there are two main approaches to this. There is a nanowire approach that is just mainly taken by Microsoft Group, that basically you start from a one-dimensional channel, you apply the magnetic field in the right direction, and you expect to see Majorana fermion at either end of these nanowires. There's a newer proposal, which came in 2017 from Copenhagen and then Harvard, that you can actually use a very long Josephson junction. So if this Josephson junction I'm showing schematically here is much longer in the x direction than the y direction, and applying the magnetic field along the junction actually gives you same Majoranas at either end of that Josephson junction. So that's the direction that we will focus, at least in this talk. And I will show you that I think we're convinced that we can see these Majorana fermions. So I said material science is very foundation of a lot of things in quantum computing, also in condensed matter physics. So we do molecular beam epitaxy of growing of aluminum and indium arsenide. Aluminum is a metal. Its structure is very different than indium arsenide, which is a semiconductor. But with a lot of optimization and using tricks and techniques, we have been managed to actually grow this epitaxial on top of each other. But what I mean is that if you look at the graph on the left, which is a cross-sectional image of this TEM image, you can see almost the atoms one by one, like the scale bar is only 2 nanometer, right? And you can also very clearly distinguish the interface between the InGas and the aluminum. The aluminums are the plane on top, and the InGas has this zinc blende structure at the bottom. So for borrowing the correlations that I mentioned in the Hamiltonian I showed you earlier, you want spin orbit and you want the Cooper pairs basically from the aluminum, you need a really good interface. And here is where actually that becomes crucial. And the material science is a must to actually get this physics to work. Also for the gate tunable qubits I showed you, this is also a necessity.
Joe, I had a quick question. This is more a curiosity question, but how much diffusion is there across the barrier from the aluminum, say, to the other side, or vice versa?
Right. So it turns out, actually, if you put aluminum directly on indium arsenide, there is a huge reaction that will happen, and you would never get an image I'm showing you on the left-hand side. To actually avoid that, and sometimes it happens, the way that the MBE is set up, is that we try to actually grow a monolayer of aluminum arsenide as a diffusion barrier between indium arsenide and aluminum. So you don't, maybe you see it here, but there are TM images that makes it more clear. If you put that layer of aluminum arsenide, then basically each layer grows differently. Aluminum grows in a 1-1-1 direction. It's like a van der Waals material. It actually has quite a bit of, it can take a lot of a strain. So it's really kind of decoupled from the substrate, which is the indium arsenide, once you can get it to that phase.
Okay, in the right, and there is in this picture in these heterostructures here, you would have this diffusion barrier of less than a nanometer.
Yes, a monolayer or two, and which is the key basically. If you don't do it, the TM image you will get, it will be aluminum eating indium arsenide on top of aluminum, which is very, once you see it, you don't believe it.
I see. So it's dozens of nanometers of diffusion. Okay, got it.
Yeah, it's actually quite a bit. Aluminum has a very high kinetic energy at the surface. So actually, when we grow this, the only way we can force it to go 1-1-1 is to grow it at minus 30 degrees. It has to be really cold. So when aluminum sits, it basically prefers 1-1-1. But the problem is 1-1-1 is 6-fold symmetric. The lattice of indium arsenide is 4-fold. So you actually get degenerate boundaries too, because it doesn't know when it should sit down this 60 degree or 60 degrees rotated. But we basically, once we grow these kind of materials, we characterize a superconductor in great details, structurally and transport. We also characterize the semiconductor independently, as I'm showing here. You look at the, you remove the aluminum, you look at the transport, mobility, mean-free pass. For aluminum, we look at the thickness dependence of critical field, the critical temperature, and obviously the grain boundaries and all that. So it's kind of part of the game.
Got you. Okay. Good. Thank you.
Yeah. So then you obviously have this material is a 3-inch material. You can make Josephson junctions out of them. So on the top left, you will see a schematic of it. You basically remove the aluminum to form the channel. And basically now the Cooper pairs have to travel through the green indium arsenide and back up to aluminum. And if you want to have the gate dependence, you actually have to put a dielectric like aluminum oxide and then a gate on top, right? So because the interfaces I showed you are epitaxial, we actually get very good response from the Josephson junction. The VI curve is shown in the middle. If you look at the inset, basically you get a zero voltage state here in this particular geometry, 5 microamp of supercurrent. And if you look at the ICRN values divided by gap, we get about factor of 2. I guess the best one we have is 2.8, which you can compare it to the textbook picture perfect 3.14 number. If it's not epitaxial, those numbers have been always 1 over 50, 0.05. And this has been a great improvement over those.
I see. And so in the current voltage diagram here, you have the nice superconducting state, and then you have several. It almost looks like a step, I guess. Do we know what that is? Yeah.
So some of those are MAR, multiple Andreev reflection. But because we are usually doing current bias, it's very difficult to actually associate them directly in voltage. But there's a paper that we have from 2016, I think, that actually studies this, and it seems they're related to multiple Andreev reflection.
I see.
Yeah. So by applying a magnetic field, you can see a Fraunhofer pattern on the lower left, and that basically shows the current is pretty much going uniformly through the junction. The lower right is the key, right? With gate voltage, you can actually kill the superconductivity or tune the supercurrent from something that looks like 5 microamp to 0 at around minus 10 volt. And obviously, the gate voltage axis depends on the thickness of the dielectric. In the research lab, our gate dielectric is about 60 nanometer. At Intel, you can do a factor of 10 better.
Yeah, I was about to say, can you help us remind us what the voltage is defined between? When you say gate voltage, it's between which two?
It's basically the tie gold on the top and the 2 deck.
The chip, yeah.
Yeah. So it's a parallel capacitor, practically. So I have a Josephson junction. Did I show the? Yeah, the dimensions here on the top left is 4 micron wide and 100 nanometer separation between the superconducting electrodes. So it's a pretty long junction. And if I apply my magnetic field in the plane of 4 micron junction, according to the theory, we should actually stabilize Majorana fermion. So with our colleagues, Alex Matos-Habiage and Igor Zutek, they have done a lot of calculations for realistic parameters that we use in the experiment. And we show that if you do not phase bias the junction, you actually do expect to see a Majorana fermion. So if you look at the left graph, you see that the spectrum as a function of By, which is basically along the long direction, and you see that the states come together at 0. If you look at the red traces, around 0.5, 0.6 Tesla, you actually form a Majorana fermion at 0 energy. If you look at the supercurrent in the device like that, basically you see that the supercurrent closes and then reopens for a p-type superconductivity. If you put this device in a squid, you should be actually able to pick up a pi phase self-tuned in the p-type superconductivity that I will show you in a second. So the highlight of the experiments we have done with these Josephson junctions are rather simple, but also very intriguing. So this is a CM image of the device that we have measured. This is in a squid geometry, but the other junction is basically depleted for this measurement. We apply By along the long side of the junction. This has epitaxial aluminum. And what you will see is that basically the supercurrent just disappears monotonically. And the reason is because we have a gate voltage on top of this device, we have tuned it to a very low value, so a spin orbit is not playing a role. And if you remember from my Hamiltonian, a spin orbit actually plays a great role in sort of a stabilizing topological states. So if I now increase my gate voltage on the same device, I should be able to see a difference in terms of how the superconductivity closes. And this is exactly what happens. So when I actually increase the gate voltage to plus 1.5 volt, you actually see the supercurrent closes around 0.6 Tesla and then reopens, and then basically it closes when the superconductivity vanishes around 1.2 Tesla for this thin film of aluminum. So this is a clear evidence that basically this reopening of the gap is very critical to sort of stabilize this topological state. And we actually can do this on multiple junctions, and we have seen a very similar physics. So if you will, you can actually do a phase diagram. So in this graph, if you sit at 0 x-axis, which is 0 bias, and then tune magnetic field and the gate voltage that I basically showed you two snapshots of it on the y-axis, you will see that at high gate voltages, for example, plus 2 volt, if I apply my magnetic field on the horizontal axis, I go from a phase that is S-type and reopens as a P-type. But if my gate voltage is too small, it's minus 2 volt, basically there is no phase transition. I just go straight all the way until the superconductivity basically disappears. So we believe that this is basically a signature of P-type superconductivity that can host my Majorana fermion. We have actually done more experiments when you can actually put it in a squid loop. So I have two of these junctions, and according to this graph, I can park one of them always at minus 2 volt, so it will always be S-type. And then I will sweep the gate voltage on the other junction to transition it from a SS to a SP measurement. So this is what has been schematically shown on the top right, and the measurements are basically shown on the bottom right. So you will see that the phase that we measure when we have SS is practically 0 across all the magnetic fields. And when we get to this transition, we think it's SP, the phase jumps to a value and hovers around pi.
And well, what causes the variations?
For the phase hovering around pi?
For the variance. Yeah.
Right. So it turns out because this is a self-tuned phase and it's not exactly biased, it's not clear whether pi is exactly the right universal number for this. On top of that, when we do these squid measurements, we are looking at oscillations. I guess you see the raw data on the left-hand side that are millitesla or smaller. And basically, the period of those oscillations are the fit that we do to extract the phase out. So we are almost fighting with magnetic Earth and all the insulations that we do. So I would expect one improvement could be basically systematic on the measurement side, that if we can basically do better improvement and have more stable devices and stable magnets, we should basically reduce the error bars. But I don't think eventually it should saturate exactly at pi. That's also shown in calculations, in simulations. But definitely there are some systematic ones. Like, for example, you look at the numbers around where jumps happen, around 500 millitesla, right? If I go back here, around when the supercurrent basically disappears, I really don't have much supercurrent to measure the phase anymore, right? When I have a lot of supercurrent, obviously I can, compare it to the other junction and actually measure a phase. But once my supercurrent is 5 nanoamp, it becomes a lot harder for me to measure a phase and exactly follow the sinusoid data. Right? So there are systematic challenges with this. But obviously, for the points around 800 millitesla, I'm more comfortable, and I think those can be corrected more systematically with a better setup.
I see. And
okay. Yeah.
Maybe this is a silly question, but the notation here, the VG2, the 2 looks like a square. Can you remind me what?
So basically, if I have a squid, we basically call one of them 1 and one of them 2. And because there are two independent gates, so VG1 changes the gate voltage on the first junction on one side of the arm of the squid, and VG2 changes the other one. So I guess in the squid graph on top, I think VG1 is the lower one, and VG2, I'm sorry, VG2 is the bottom one, VG1 is the top one.
Okay, good.
That's why the VG2 changes S to P on the top right. Yeah. And for this, for example, graph, VG1 is always at -2 or -4, some small number that actually prevents it from doing a transition in magnetic field. So with this experiment, more tilted measurement, the gap closing measurement, we are very convinced that we are actually creating this topological phase that can host Majorana fermion. But as I showed you earlier, I was making a case that, without moving them, without braiding them, without knowing this is non-abelian, we haven't made much improvement, right? We really need the answers to those before we can even attempt making a qubit, right? So there have been proposals of how to do that. 2011, Jason and Lucia had this keyboard idea that if you have a nanowire and somehow you can tune the chemical potential with the small gates under it, maybe you can actually change the length of the nanowire digitally by this gate voltage. And if that's possible, then you can also make multiple Majorana fermions, like part C of this graph, that you can have, pairs of Majoranas by activating the gates properly. So we can import that idea into our Josephson junction, right? Because in our Josephson junction, right now we have one big gate. If I can make that big gate into multiple small gates over the junction, I showed you that the gate voltage plays a very big role. Like when they are positive, they have a transition. If they're negative, it's just S wave. Then I can make two pairs like gamma 1, gamma 2, and gamma 3 and gamma 4, and then bring them together and let them interact and then go back. So this is like a Rabi oscillation almost, to sort of see how the Majoranas interact. So if I can do that, that would be great. So this is a better, maybe a schematic that it shows on the top right what I showed you. That was a single junction with a gate on top. When I applied the magnetic field with the right gate voltage, we saw topological transition. And now what I want to do is that make that one big chunk of gate into smaller gates, as is shown in the lower right. So if I do that, then I can actually tune the left two gates, for example, to the green. That where we basically support Majorana fermion, the top two right on the green, and then that would be another pair, and then they can interact with distance, right? So that's kind of the big idea. We have actually now are making these devices. So I'm showing you an SEM image of an actual device. The little, I guess, gates in the middle are the mini gates that basically are schematically shown on the right-hand side. That's where you actually expect the Majorana phase stabilizers if the gate voltages are correctly put. And then for this particular device, you see two quantum point contact on either end of the Josephson junction that actually does the readout part of this circuit. So we are doing these experiments, and I can show you sort of quick control experiments that you can activate. For example, on the top left, you see that I have made the colors crimson for the either end of the gates, and I've depleted the middle ones. And obviously, you like to see a squid data, as the current can only go through those two junctions. And that's what is shown actually on the top right. On the lower left, we activate another two gate, and on the lower right, we prove that also that is basically a squid data. So basically the gates work, that you can do multiple gates. Now you have to apply magnetic field, stabilize Majoranas, and that's what we are exactly doing right now. I guess my time is just kind of coming to an end. So I want to switch gears and tell you about another super exciting idea and then try to wrap it up. So I think with the gate control, we are marching our way to do the first movement of Majoranas and then the braiding. We always need the magnetic field, right? But somehow, if I can get rid of this 0.6 Tesla, that's also a great advantage, right? And the way that we have an idea to do that, and there is a paper in PRL here, you can read more details on it, is by looking at the X junction. So here you will see an SEM image of an X junction. So the gray is where basically the indium arsenide is, and the blues are the aluminum. And basically all the contacts are looped around each other by phases phi 1, phi 2, phi 3. And we can show, we have a recipe that actually says, if you stabilize a Majorana by applying a magnetic field in the plane, you can actually basically move the Majoranas by changing the relative phases. So basically, if you ramp phi 1 from 0 to 1, you can basically do one rotation of Majorana. You basically now change phi 2, you change phi 3. So this is like flux line tuning of those little loops. But actually, then you can control the movement of Majorana. I think on the lower right, I have the cartoon version of this as phi 2 is changing through the spectrum. And you see that's how the Majorana is supposedly going to move around.
This is the theory part now?
So this is the theory. This is the theory that we have made devices, but they're not measured. I mean, this is more complicated than the gate ones because now you need a lot of fluxes and you need full control. And but from the theory side, it looks like a very good way to actually manipulate and move the Majoranas. So basically, we have two distinct ways. One is with phase, we can move Majoranas. With gate voltage, I can also digitize the system and move the Majoranas. Experimentally, we haven't shown we can do that yet, but the devices and ideas are all there, and it's a work in progress right now.
And I guess it's a little tricky to decouple all the fluxes also, so you only move one and not the others.
Exactly. Yeah. Exactly. On this one, I mean, we have a protocol, but the realization of it, I think, is much more difficult than the gate version. With the mini gate, at least you can create two Majoranas. Here, the system is one system, and you have to always solve the solution for all this, the whole package, basically. You cannot isolate it. So for now, we are working actually
And
on
how
the
much crosstalk is there? I mean, the flux tuning knobs usually have a decent amount of mutual and coupling and crosstalk and
Right.
DC gate voltages, especially at small scales like this. How much?
Oh, I'm sorry. This is not to scale. So the SEM image is to the scale.
Yeah,
Of course. Definitely not to the scale, right? So the basically flux lines are about 100 micron away from each other. And those phi 1, phi 2, phi 3, the only thing you need to do is to go to pi, basically to pi. And for those, it's basically we are borrowing the existing technology from flux qubits.
Yeah.
And for that, I mean, there is some flux noise and everything. Here for Majorana, you can argue the time escape, right? So basically on the lower left, I'm showing you a typical graph of the spectrum. So you have to be faster than the quasi-particle poisoning. That's estimated to be 1 millisecond. And adiabatic, I guess, compared to the gap, you see the blue lines are coming together. So you have to be faster than that. And that one is about the nanosecond. So basically the ideal time scale for these systems is about a microsecond. So with gate voltage or flux, you want to be in that regime. But I think for both of them, this time scale have been shown before.
Yeah.
Right. With fluxes, definitely you can do up to 100 nanosecond easily.
Yeah.
So, I mean, lots of ideas, lots of progress. To me, at least, we are making devices that are not doing non-trivial operations, just beyond showing that there is a Majorana fermion. And obviously, you get to higher level, you have to think about, I want to do a X gate. How can I do it? I need now to basically make 4 Majoranas, starting braiding together. So we have architectures for CNOT and how you can actually make it out of these gated structures. I'm not going to go through the details just because, I mean, we don't have it yet. I wish, but I'm very hopeful in the next 6 months that we will have some new updates on this. So I also like to highlight the summer camps that we have had in last year and this year. We had about 20 students that actually come to the lab, do an experiment on some sort of a project in the lab, whether it's material science, whether it's microwave, maybe it is a fake qubit that we actually make and then try to control it. And also thank to IBM for people actually doing a lot of quantum programming with available hardware at the cloud. And I think for younger students who are brave and unorthodox, they enjoy it, the fact that you don't have to kind of go through all the details on the hardware side and you can immediately get access and kind of do an actual quantum algorithm and then sort of see how it is. So let me just ask one question and try to answer it if I can. So will the future qubits or whatever that will win be topological? Because I said, if we make topological qubits, the error is one qubit. One topological qubit is practically one logical qubit. Then you need 50 of them and you're in a great shape. If you do the tunable ones, you need billions of them, and maybe that's the way to go. The fixed frequency qubits, maybe that's the way to go, right? If you go back to the invention of transistors, which was in germanium, and this is a photo from 1948, it got actually commercialized, and it was sold in many different avenues, especially in the Army, for 10 years, before people realized that, silicon transistors can do better. And almost in a few years after it was realized that silicon is a good candidate, the whole market was taken over by silicon, right? So whether for quantum computing, something like this, we have a magical solution or there is a hybrid solution, I think it's hard to say. But what we can do as condensed matter, I guess, people and who have interest in quantum computing is to kind of get guided by the theory, do the experiments, we fail, we learn from each other in a non-trivial way, and then we kind of feedback this and we make an ecosystem. And so far, I'm very excited about this field and hopefully more will come. Thank you.
Excellent. Thank you, Javad. This was absolutely great. We have a few questions from the audience. Okay, well, this one is interesting. It's a bit tricky, so but I think it will be curious to a lot of the listeners, and I see there's a discussion happening on it right now. It's how does this relate to the approach people have heard about from Microsoft that have been pursuing may or may not have succeeded with braiding, and what's the difference between this and similar? Can you give us some relationship?
So my personal opinion on this is that let me go back here. So I think there has been great amount of progress in terms of looking for what we think is Majorana fermion, right? I showed you evidence that we think that we have a topological superconductor. Can I prove it? I think the only proof to me is to show that this is non-abelian. Maybe it is something else. Maybe it is super exciting and we don't know what this physics is, and later on we find out what it is. If it's not non-abelian, and if it is abelian, it's not as exciting, right? So in Microsoft, in the nanowire approach, there are a lot of, I guess, papers and news and views that the Majorana have been discovered in nanowires. I mean, maybe, right? I mean, there are great papers on that avenue, but nobody has done anything toward moving them. Nobody, I think, has done anything regarding braiding, and definitely nothing on the non-abelian case, right? So those things are kind of the minimum information that you need. Or you try to fuse them together, right? If you fuse the Majoranas together, there is a, if you basically fuse two fermion, you just basically get nothing. But if you get fusing two Majoranas, half of the time you get an electron, half of the time you get empty. So if you can show that a statistic, I think then we are getting serious about it, right? And I don't think if Microsoft is basically beyond having proof of, the detection of Majoranas in nanowires, very similar to what we have done. But I think the next step is the most exciting step.
Mm-hmm. Yeah. Thank you. And I'm reading the question here. 1 second. And maybe while I pull that question up, a few slides before that, you had an introductory slide of fixed frequency versus tunable with DC gates.
Mm-hmm.
Yeah, I think this one. Yeah.
Yeah.
Right. So I guess there is, of course, also the flux tunable parts, which you mentioned later. So can you say a little bit more about what are maybe some of the advantages or disadvantages of using the DC gates in this kind of pinching mode versus the more dispersive superconducting mode? And
right. So I guess, as I mentioned with the gate, the first thing is easy in the sense that you can operate a gate very fast. It's just electronic. You just need a voltage.
Yes.
So you can tune that. The other thing is the power consumption is zero, practically, right?
Right.
In a SQUID basically tuning circuit, you basically have to have a flux line, send a milliamp DC or pulse, and then you basically get a coupling. That coupling could be a strong or a small, depending on how you want to run it. And you are sending a milliamp of current into a dilution fridge with a millikelvin temperature, right? So if you scale up, eventually you will run into trouble. I mean, people are always smart, right? You all find answers to all of these questions at one way or the other. But at the face value, a SQUID seems to me slower and also consumes a lot of power when you scale up, and it will be a problem. With the gate, you don't have those two problems. In a SQUID control, you have flux noise. Here you have charge noise through the gate. Which one will turn out to be worse or better? I think we really need to look at it. The reason that the gate mons or this tunable qubit have not really taken off is that so far, as I showed you, I can only do it on indium arsenide. And indium arsenide, the 3.5s in generally are piezoelectric. So they're always the absorption, you're starting from a bad point. If we can do this in silicon, then I think we are comparing apple to apple.
Yeah, I see. So you mean that their loss tangent intrinsically is 10 to the minus 4 or something pretty poor to begin with.
Exactly.
So even the single photon in the qubit is going to get dissipated pretty quickly. Although I might say that I would think that flux tunable gates or qubits can operate at the 20, 40 nanosecond, so they can be pretty fast too, because it's also in a sense, well, we say DC, but it's
yeah. I mean, that's the thing. I guess that field is a little bit more advanced than this. So at the beginning, it was limited, but now people have done like great improvement, right? And you can even handle the power at the dilution fridge, at least for tens of qubits. For this, I think it's much more, it's just younger. So we haven't really done that much. We haven't optimized the gate stack. We haven't done, changing the substrates and all that. But I agree. I mean, the squeeze you can do 10 nanosecond easily now, maybe even faster.
Because you can have superconducting, basically coax lines going from your 15 millikelvin up to 4K, where you can dump a larger thermal load and things like that.
Exactly.
Yeah, and then sorry, let me see if I'm so there's a question here. Curious, how do you etch the aluminum and stop at the aluminum arsenide interface without damaging it?
Right. So there is actually a great etchant. Let me see, where was the schematic here? So there is a selective etcher basically that etches aluminum and not indium arsenide. I had it somewhere here. Yeah, here. So you basically open this gap where I want to remove the aluminum, and something called Transient D aluminum etcher is perfect for removing aluminum and not touching indium arsenide. If I change the aluminum to niobium, then I have a new problem, right? You have to find another magical solution. But for aluminum on indium arsenide or aluminum on silicon, these magic solutions exist.
I see, and it doesn't seem to damage or increase the roughness of the surface or any of this stuff.
It doesn't do that. You get a slightly like 5 to 10% increase in the density of indium arsenide channels. So something happens at that interface. It's not perfect, but it's not substantially different.
Ah, I see. In which channels can you?
So when I look at this Shubnikov the house, and if you look at lower right,
yeah,
I can measure the density, right? And I can grow a structure without aluminum, and I can grow a structure with aluminum and then remove it. And what I usually find is that the one that has had fab on it, or basically had the removal of aluminum, the density, for example, at 0 gate voltage is 10-20% higher than the ones that I don't grow aluminum on at all.
I see. So,
and if you're not careful, it could be actually quite wild. But now with optimized process, I think it's 20% is reasonable.
I see. And so in these junctions, you typically have on the order of thousands of channels?
So now 400 or 500, I want to say.
400 or 500.
For the dimension that we have.
Right. And the average typical transparency is sort of at the 10 to the minus like 2, 3.
So there are two transparencies, right? If you want to get to the detail. One is that the interface transparency. That one is very high. And one is for the junction transparency, right? For Andreev states. And for the junction transparency, which is more relevant, we usually get 0.9 plus minus 0.1. So it could be awfully good or not. I mean, that's the error bar. I cannot do better than that. But for the contact transparency, we can get 99.
99.
Yeah, I mean, with some reasonable error bars.
And then, but for each conduction channel, if I think of it that way, or is that a bad?
That's very hard. That's very difficult to kind of know. I mean, basically from some Shapiro step experiments, what we find is that 10% of the modes have almost near unity transparency, and the rest do not.
Oh, okay, so it's very, I see, because in a typical Josephson junction, you usually have basically all of your, maybe 500 to 2,000 at most channels, and you have, I think transparency is at the 10 to the minus 3.
That's right, very low.
10. Usually you don't have any modes or any conduction channels that have near unity, because then you get also quasi-particle poisoning of those channels, and that can shift your inductance. So how much is that an issue here in terms of the stability of the junction of these types of junctions versus time when you get quasi-particle poisoning and all this stuff?
So I guess there are two different things, right? For a gate mon, you don't want a very wide junction, right? Because for the gate mon, I only need 5 nanoamp of supercurrent. Here on this graph, you are seeing 5 microamp, right? So for that one, we have to really shrink it into almost a nanowire, right? And there, you basically go back to a small number of modes, and then you can tune the transparency with the gate voltage too, or by the design. You can basically put a barrier between aluminum and indium arsenide to actually decrease the coupling. For the Majorana fermion, I need the best interface and the best proximity effect, because that's what is my upper bound in terms of the topological gap. And for that, we haven't done any fast measurement, but the estimates from the theory interpreted data is basically this 1 millisecond quasi-particle poisoning. But I'm sure you have to do a lot better, with the gold traps and all that. Those should help, because especially for this particular design.
Yeah, I see. And getting back to some of the other questions, I see there was a follow-up to the earlier question on the etch. I guess they're saying it's a wet etch, to clarify.
That's right.
Great. And here's another question. Is the indium 0.5 arsenide 0.5 doped?
No, for our structure, I don't know if I'm showing it here. Let me see. Maybe I'm not showing it. So the structure that we have is indium 0.8, aluminum or gallium 0.19, arsenic. It's not a lattice match structure. No, I don't have it here on the material science part. So basically, it is not the lattice match structure that people usually grow to indium phosphide. What we do is that we grow a lattice match structure to indium phosphide and then subgrade the indium composition to a high number because we need to grow a strained indium arsenide on top of that structure. So if you're interested in the growth modes, these 3 papers actually are pretty good papers in describing that.
Wonderful. And this might be the last kind of open-ended question here from the audience. Any word on the scalability of these topological structures and so on?
So yes, so okay, so a structure like, I guess the devices like this, let's say everything is positive and we are successful and this is indeed Majorana with non-abelian, these are really big ifs, right? And let's make another big if on it, that if we make a qubit, the coherence and the error is really 10 minus 6 in a standard way that we are thinking, right? The scalability of this is not going to be great. That's very obvious, right? I can maybe make 50 qubits, and that would basically take me 500 DC wires and RF coax lines and all that. But if we are at that level of 10 minus 6 error, 50 qubit is pretty much what I need to have the most powerful computer with all the ifs that I mentioned, right? If it turns out that this is also a 10 minus 2 qubit, then the scalability is a big issue, and then maybe this is not the best way to go. And I had this discussion with my grad student, and he was saying even if we find that this is not working, it still is a great answer. I like that answer.
That's good. And speaking of gate fidelities and so forth, I mean, the Majoranas are topologically protected in many ways, but there's still some things that, as far as I understand, I don't know a great deal, but as far as I understand, they're not protected against things like, again, quasi-particles, or there are certain things that will limit their lifetime, so to speak.
So one fundamental problem is that the Majorana gates are not universal. So out of the 4 gates, you only have 2 with Majorana that are topologically protected. So you have to actually do a lot of distillation, which puts, again, another huge overhead over the whole problem, unless you find a very curious problem that doesn't need that enormous amount of distillation. So these are all active research. But I guess from a condensed matter point of view, having these particles would be phenomenal. Seeing non-abelian physics is great. And then, again, I had that, I guess, picture about the future. That you're all looking in the flat. I think that's exactly
very poetic. That's very poetic.
Like in next year, maybe we talk again, and I have this under control, and I have multiple Majoranas, and I know something better.
Yeah.
And then, but maybe also we know more that this is difficult, right? As it stands, even if everything works, Majorana still is going to have a huge overhead on it for a full quantum computing algorithm.
Yeah, that's very interesting. Okay, good. I mean, seeing as we are coming up, we have had lots of questions here. I don't know that the slides will necessarily be posted per se. There's a question from the audience, but certainly the talk here will stay online, so you can browse through the talk. And I think I also forgot to mention at the beginning of the talk that I would like to thank Javad for being a great host. Last time he invited me and hosted me at his lab at NYU. So thank you for the invitation and being a great host to everyone, to all the lab members as well. I'd also like to open it up if you have any final words, Javad, for the audience or for folks who are interested in getting to know more about this research or coming into the community, or any final thoughts you have.
No, thank you. Thanks, for giving me this opportunity. But I want to emphasize this slide again. A lot of us are doing different physics, different material science, different research fields, maybe even working, on Wall Street and others and software companies. There is always a way to connect to quantum computing. I think that's the beautiful sense of this. That you're writing a compiler. We need a compiler that is more efficient. You're a device engineer. We always need engineering a device that controls the microwave. From the physics part, if we can discover something new, I guess I showed you one example. Maybe it shortcuts everything, right? Material science is a must. The better material we make, the better the systems are going to be. And as a material scientist, maybe you do not have an immediate path to kind of it's not obvious for all of us that how we can be a quantum computing contributor, but I think they can reach out, and there are lots of resources now that are coming in from even younger age that you basically learn the stuff that are going to be immediately useful for this. And again, it's one of those things that this will make an impact, unlike just be pure science.
Yeah, absolutely. And like you said, there are more and more resources. I mean, recently we did the Qiskit Summer School. I know many of the audience members here went to that, and I think they'll recognize some of the slides you showed at the beginning sort of overlap very nicely with that. You know, those are resources that didn't exist, I think, maybe when you and I had first the chance to get into this, but you can, like you said, get in much more earlier now, and there's so many different avenues that tie in. So that's exciting.
Absolutely.
So with that, I'd like to thank you, Javad, for being our distinguished guest today, and I'd like to thank the audience as well for tuning in. We would love to see you back next Friday, noon Eastern time, and this talk will stay recorded, so you can go back and tune it. I will have, I think, a link to Javad's lab and papers and so on, so stay posted for those. And thank you very much, everyone, and see you next week.
Thank you.